Good morning, my dear kids. I'm Sridhar Reddy, physics lecturer. So, in today's class, we are going to discuss about in the ray optics chapter, refraction at the plane surfaces. If you can recollect, in the previous videos, you might have come across like the reflection at the plane mirror, then reflection at the curved surface. The next topic will be the refraction at the plane surfaces. In that, we are going to discuss today the theoretical aspect of the Snell's law of refraction. What all we discussed this Snell's law of refraction. It is some sort of like a very basic for the rest of the ray optics. What we are going to carry on that one. When you go for the prism, or when you go for TIR, or you go for when you go for the lens concept or refraction spherical surfaces. In almost all the situations, the basic Snell's law will be applied here. So first we'll uh, bring the what is the Snell's law? We'll derive the Snell's law. Then we'll go for the application of Snell's law. Then we'll go for the numerical part of the different situations how that basic Snell's law can be applied here. I think this is the core central, you can say the topic of the entire the ray optics what we are going to discuss. The ideas here what you're going to learn will help you a lot in the coming chapter, coming topics of like prism or the lenses. So let me begin the class. So as you know, the ray optics, which was the most essential thing what we have learned so far is about the in the ray optics, the most essential what we learned till now, it was about the reflection of a light. Now, the next property of light we are going to discuss is what? The refraction of light here. So refraction of light, this one, means when a ray of light moves from one medium to another medium, when a ray of light moves from one medium to another medium, it bends. It bends or changes direction. Changes its direction. So usually, if there's a medium, there's a normal. If the ray is propagating, either it may bend, there's a refracted ray, I'll show it. This particular thing is what? This is the incident light, there's a refracted light. There's incident, there's a refracted. There are two possibilities of this. There is medium 1, medium 2. There's a medium 1, medium 2. So we have to give specific reason why do the light will bend as it propagates from one medium to another medium. That particular explanation, the conclusion of that is what will lead to the Snell's law. Okay, let's begin our discussion from here. Suppose when if a light propagates in space, then F equal to C lambda naught you are going to write, or lambda, let it be this one. So what is the C? Speed of light. Speed of light in vacuum. What is lambda? Wavelength of light. F will become the frequency of light. This frequency depends on source. The source which will generate the light, it is going to determine this particular the frequency. Whereas the speed of light and the wavelength of light depends on the medium. In vacuum, it will be equal to C, and approximately we'll write this as 3 point into 10 to power of 8 meter per second is the speed of light in the vacuum. Then depending upon the particular spectrum, it will have the different frequency and the corresponding wavelength it is going to possess here. Now the same light, when it propagates in some medium, when same light, if it propagates in medium, the equation for that will be F equal to V by lambda dash, we'll write it. What is V now? V will become the speed of light in medium. V will become speed of light in a medium. What do you mean by medium? Medium can be water, can be glass, or anything. It can be other than vacuum. Then lambda dash is the wavelength of light in the medium. Then this particular speed of that one, it is given by this one, mu, this expression, where mu is called as refractive index of medium. Different mediums, the value of mu will be different. For different medium, the value of mu will be different. The refractive index of medium. Suppose a glass 1.5, a water 4 by 3, the diamond 2.5. So like that, based on the material, the refractive index will be different for different medium, and it depends on density. We can see here. Now, as the mu increases, the speed of light decreases. So like this, we can categorize the mediums based on the refractive indexes here. So now how we can say medium is denser or rarer? Where the speed of light is more, it is said to be, the medium is said to be rarer. Where the speed of light is said to be more, it is, okay, let me put it in. Where the speed of light is more, the medium is said to be rarer. Where the speed of light is less, the medium is said to be denser here. Because as the mu increases, the speed of light is going to decrease. Or if mu decreases, the speed of light increases. So like this, we can categorize the mediums rarer or denser based on the propagation of speed of light. With what speed the light propagates in medium, that is going to determine the particular the rarer or denser of a medium. Now let's do one thing. Let's take a medium one. Medium one, where refractive index mu1. The light will propagate with a speed v1. Here, what is the equation we can write? C by mu1. Next, let me go for the other medium, medium 2. The refractive index of this material or this medium, let it be mu2. Here, the light will propagate with a speed v2, where v2 I'll write C mu2. Then if I put mu2 greater than mu1, let me put a condition, mu2 greater than mu1. And then what conditions? Mu2 greater than mu1 means v2 less than v1. So where the speed of light is more, it is more in the first medium. So this medium 1 is said to be now rarer, this is going to be denser. On what basis? On just this condition. So now this will become rarer, this will become denser. Now rarer, denser is some sort of relative. Compared to medium 1, medium 2 is denser. Now I can bring another medium where the speed of light in that medium will be less than the medium 2. Then compared to the third medium, this will become the rarer. So these are not some sort of like an absolute denser rarer. They are some sort of like a relative. When we compare two mediums, so this is going to, with the help of this, we are going to categorize. With the help of the refractive index, we can now categorize the mediums, whether it's a denser or a rarer. Okay, let's go for further discussion. Suppose if you have let me use colors. So there's a medium 1, medium 2, there's a medium 3. Here mu1, mu2, mu3. Speed of light here v1, v2, v3. Now let me put a condition like v2 greater than v2 less than v1. And we know what is the formula, c by mu1, v2 equal to c by mu2, v3 equal to c by mu3. If v2 less than mu1 means mu2 must be, let me put that one. So let me first condition, let me put it here, v2 less than v1. So what does it mean? If v2 less than,
incoming call from Ecart Logistics.
okay, let's assume that three different mediums. So what I have displayed here, then mu1, mu2, mu3. There are three mediums are the medium 1, medium 2, medium 3. So let me indicate here. There's a medium 1, medium 2, medium 3. Speed of v2 let be greater than v1. So with v2 less than v1, so mu2 greater than mu1. So where the speed of light here, the condition is a mu2 greater than mu1. So speed of light here, mu2 greater than mu1. So speed of light in the second medium will be less compared to medium 1. So then I can put a condition that based on this, medium 2 is denser than the medium 1. I'll put further a condition, let v3 less than v2. In that case, mu3 will be greater than mu2. Medium 2 is denser than medium 1, and we can conclude that here medium 2 is denser and medium 1 is rarer. Here if I further put a condition that v3 less than v2, if v3 less than v2 then mu3 greater than mu1, then speed of light in the medium 3 is less compared to medium 2. Then what is the conclusion we can make? It is like a medium 3 is denser than I'll write with respect to medium 1. Here is denser with respect to medium 2. What is the conclusion we can make it now? Medium 3 is denser, medium 2 is rarer. So is this denser, rarer? Are they absolute? No. Compared to medium 1, the medium 2 is denser. Compared to medium 3, the medium 2 will become rarer. So the medium 2, if I compare with medium 1, will become denser. If I compare with medium 3, it will become rarer. So like this, a given medium, we can say denser, rarer with respect to some other medium. This medium 2, what is it? Is it denser or rarer? No, I can't say. It's not absolute. Denser, rarer is not absolute. It's a relative one. We can compare whether a given medium denser or a rarer relative to some other medium. So therefore we use word like a with respect to. I think this is with respect to or relative to, either of one, with respect to or relative to. So like this now we can study the propagation of light in various mediums. There's one basic difference what we can make it here. Now, what will happen to the other parameters of the light as the light propagates through a medium? What will be the other parameters? What do you mean by other parameters? Means like the frequency, the wavelength, because the speed of light will change as it propagates from one medium to other medium. anything will happen to its frequency and wavelength. No, the frequency of light depends only on the source. As the speed of light changes, definitely the wavelength of light has to change. So here only we can write it here now. Suppose F equal to V by lambda. V further we can write it as C by mu. Then F equal to C by lambda naught. Okay, I'll do one thing. Let me put it here. It will be much convenient for you. No, this is thing. So F by C equating these two. So F equal to, I'll substitute this here. So C by lambda naught equal to C by mu lambda. Lambda equal to now lambda naught by mu. What is lambda naught? Wavelength of light in vacuum. What is lambda? Wavelength of light in medium. So in different medium, the speed of light will be different, the wavelength will be different, the frequency is going to be same. So this is for in vacuum it is. In any medium, there is a formula. Okay, speed of light, like how the frequency and the speed and the wavelength of light is in any medium is given by F equal to V by lambda. In vacuum, F equal to C by lambda naught. Then how that wavelength of light in different mediums are related in terms of refractive index, we'll make it a generalized formula like this here. Can we say anything about the wavelength of light here? Because the frequency is going to remain same. If speed of light increases, then the wavelength has to increase. If speed of light decreases in medium, the wavelength has to decrease. So what we can write here? Lambda 2 less than lambda 1. Or here only I'll write it. Lambda 2 less than 1, lambda 1. Now what about here comparison? V2. So here lambda 3 less than lambda 2. The next question comes like speed of light changes as it propagates, as it moves from one medium to another medium. Wavelength of light is also going to change as it propagates from one medium to another medium. What will the frequency? Frequency is going to remain same. It depends only on the source. Okay, one more parameter called like a visible light. If you take it, something the color is what very essential one. When you take the visible light, Vibgyor, we can take example of the visible light Vibgyor. So in the violet color ray of light as it propagates from one medium to another medium, anything will happen to that color. Yes, the color is a parameter of frequency. So definitely the violet color propagates from one medium to another medium. Yes, it is going to remain as violet only. Okay, this one. So this is about the basic idea of the when a ray of light propagates from one medium to another medium. Okay, let's go for the some small basic idea based on these things. Some small related numericals we'll discuss. Then I'll start the Snell's law, which is very much required for us. Okay, let's take this question. Two transparent slabs are of equal length. One is made up of material of A of refractive index 1.5. Okay, this is having the refractive index 1.5. Then other material of B and C are ratio of thickness 1:2, something is done. The refractive index of C is 1.6. Okay, there's a refractive index of C. I'll give a better diagram. So we have this is one slab. Next we have other slab, and this is slab C. Now the length of other one is more than this one. Okay, proportionally I am changing the dimensions also. Okay, this is the condition. Okay, you see this one now. Two transparent cells are of equal length. One is made up of material A. So the length of this is equal to, I think, oh, yeah, based on the question, I modified it. So the length, this length is going to be the same. Then again, this length is L, this is 12. I think if you read question, so there's a A, there's a B, this light will propagate here. The refractive index of this is mu A 1.5, mu B we don't know, mu C it is equal to 1.6. When light passes the two slabs have the same number of waves is telling. Two slabs, what do you mean by two slabs? Slab, this is one slab, B and C, the combined B and C will become another slab. The number of waves in this must be equal to this one. So what do you mean by number of waves? So we will start thinking like this. This is one wave. And again, in different waves, in different medium, the wavelength has to be different. No, what is one lambda 1? This will be lambda 1. Lambda 1 or lambda A. Lambda B. This will become lambda C. Number of waves on this be NA, NB, NC. They are the number of waves. So whatever the condition given for this, like a number of waves in the slab A should be equal to total sum of total number of waves in the slab B and C. So the first primary equation we are going to write it is NA equal to NB plus NC. Call equation 1. Then what is telling the length is equal. So what is this length is equal to? Number of waves in NA into lambda A, because this is one wavelength. Like that, there are some NA number of waves are there. So what are NA, NB, and C? They are the number of waves. So therefore, the length L is equal to on the left hand side. This should be equal to number of waves into wavelength of one wave. So there are some, let's assume 4 waves are there. So what you are going to write? 4 times into lambda A, this particular length. So therefore, this will become NA lambda A, NB into lambda B, NC into lambda C. What do you mean by lambda A? Lambda A should be equal to lambda naught, wavelength of light in vacuum. This everything is in free space or vacuum, you can write it. This is the wavelength of light in vacuum. Now it will enter into medium. In different mediums, it should be different. So this is given by mu A. NB equal to lambda naught mu B. NC equal to lambda naught by mu C. So NA by mu A, NB by mu B, NC by mu C. Lambda naught is, so sir, what is lambda naught? Lambda naught is wavelength of light in vacuum. In any medium, it will be lambda times omega. Already just now I discussed it. Huh? Now, what is, let's come for this one. Look at the slab B. Here slab B, what we can write, L should be equal to NB into LB. NB into lambda B, this one. The length of this slab should be equal to, L should be equal to number of waves in the slab B into wavelength of light in the slab B. At the same time, what is this 2L should be equal to NC into lambda C. What is this length? 2L should be equal to number of waves in the slab C into wavelength of light in the region C. Let me substitute the value of L here. So 2 times of NB lambda B NC lambda C. What is lambda B? Lambda B is lambda naught by mu B. NC lambda naught by mu C. So therefore this 2 should be equal to NC mu B by NB mu C. Now, or let me write expression for NB something. Okay, this will become NB equal to NC mu B by 2 mu C. Any equations, can we write it here? I'll substitute this 2 and 3 equation, 2 and 3 in 1. The unknown is mu B. The unknown is mu B. So this Na shall we write it as NB plus NC here. So put 2 and 3 in 1. Then substituting that, Na should be equal to, we'll do one thing, substitute 1 and 3 in 2. Now what is Na? NB plus NC by mu A equal to NB mu B plus NC mu C. What is NB? NB is equal to NB plus NC equal to mu A by NB by mu B plus, we'll do one thing, NB will write in terms of NC. The further solving this, I'll end up this as NC mu B by 2 mu C plus NC equal to mu A by mu B. NB will be NC mu B by 2 mu C plus mu A NC by mu C. Altogether NC will get eliminated. So the final equation will be mu B 2 mu C plus 1 is equal to, here look at this mu B by get cancels. So here mu A mu C, so mu A by 2 mu C plus mu A by mu C. Further solving this, mu B by 2 mu C plus 1, this will become 3 mu A by 2 mu C. Mu B is unknown thing, so mu B, let me substitute, I think we have all the values now, y2. Mu C is how much? 1.6 plus 1, 3 mu A is 1.5, 2 times of 1.6. Solving this, we'll get expression for the mu B. Okay, let me, 3, this will become 3 into 15 by 2 into 16. Further I to simplify, this will be 3.2 equal to 45 by 32 minus 1. 45 minus 32 will be 13 by 32. Mu B will be 1.3. So this will be our answer. This is one very, to bring the idea that in different medium, in different medium, the speed of light will be different and the wavelength will be different. Okay, and the complete problem, let me display. Okay, now do make observation. What is this primary? This is the given thing. Huh? This is a primary thing which was given for us. Number of waves in the slab A should be equal to sum of number of waves in the slab B plus slab C. Okay, this is the thing. Then the length of the slab B is, or the length of slab C is twice that of the slab B. So L to L. And the length of this slab A is equal to sum of the length of slab B and C, the combination. That only we just explored all these things. This is a given, this is a given, and even this also given. So the given things is what I'm just highlighting in the with the yellow color one. So with the help of that data, we are able to calculate the refractive index of the slab B. This is like you can ask questions. So what is this like? What is this length? Length of the slab should be equal to number of waves into wavelength of light, because the wave as the light propagates. I'm just taking help of the wave nature, little bit easier for us. So the length of the slab should be equal to number of waves into wavelength of light, that one. In that way we have expressed here. Okay, let's take the symbol one more. Consider slabs of three media A, B, C, and are arranged as shown in figure. Refractive index of A is 1.5 and that of C is 1.4. If the number of waves in A is equal to number of waves in the combination of B and C, find the refractive index of B. This is unknown thing. So there's a monochromatic light is entering the slab. As the light propagates in different mediums, it will have different wavelength. With the information of this, the data given, we should calculate the refractive index of this slab B. Again, we'll go for similar way, the construction. Now the light will, let lambda not be the wavelength of light. Here the same thing, this one, the waves, let's assume here in this way. Now what is one wavelength? So you are definitely going to take this as one wavelength, lambda A. Here this is lambda B. This is lambda C. So this is CBE. Number of waves here B NC, here B NA. Number of waves in this slab B NB. This is data given for us. Let's get into refractive index of mu C. This is mu B, mu A. The data what given, that we have put it here now. Now, what is the condition, precondition given for us? The number of waves in the number of waves in A is equal to number of waves in the combination of B and C. So first equation, I'll proceed here. Number of waves in A is equal to NB plus NC. This is a given thing from here. If the number of waves in A is equal to number of waves in the combination of B and C, then refractant. And the length of this B is, length of the slab C is twice of the slab B. So how do I can write it? So what is 2x is equal to? First, what is x is equal to? X should be equal to NB into lambda B. 2x must be equal to NC into lambda C. We have to calculate the refraction index of this particular thing. So how these two are related? So let me substitute here. 2 times of NB lambda B NB lambda B should be equal to NC lambda C. Lambda B is equal to lambda naught by mu B. NC should be equal to lambda naught by mu C. So 2NB by mu B should be equal to NC by mu C. Keep this, let this be equation 1, this be equation 2. What is this? Looking at this slab, what can be the length of this slab A? Should be x plus 2x, 3x. So looking at slab A, this 3x must be equal to Na into lambda A. So 3x equal to Na lambda A will be lambda naught by mu A. What is lambda naught? Wavelength of light in vacuum. In medium A, it will become lambda naught by mu A. In medium B, it will become lambda naught by mu B. In medium C, it will become lambda naught by mu C. So this 3x equal to, oh, it is there. Now, what is x is equal to? We have this particular relationship. So here, let me write x is equal to 3 into NB lambda B equal to NA lambda naught A mu A. Lambda B is equal to lambda naught by mu B. Three NB NB in terms of, okay, C in terms of NB, A in terms of NA, or if you solve for this, NC is equal to 2NB mu C by mu B. This equation will be Na is equal to 3NB by mu A by mu B. Let me choose this as equation 2, 3. Put 3 and 2 in 1. Let me substitute the 2 and 3 in 1. So what is Na? Let it be as it is. Na is equal to 3NB by mu A by mu B. This will become NB plus, what is NC? 2NB by mu C by mu B. NB gets eliminated, so 3 mu A by mu B equal to 1 plus 2 mu C by mu B. What are known things? Refractive index of A, 1.5. That of slab B, we don't know, 1 plus 2. Refractive index of slab C is 1.4. 1.4, this is mu B. 4.5 mu B plus 2.8. .7. Just cross check. It should be so refractive index of slab B will be refractive index of slab B will be 1.7. So this will be our answer. Okay, this is some basic preliminary ideas of the if a ray propagates in a different medium, then the wavelength, then the speed of light is going to be different in different medium. The frequency is going to be same. So based on that, some numericals is what I have explained here. Okay, now we'll take the derivation of the Snell's law. So let's start with the, suppose say I have a medium. If the light wants to propagate from point A to point B, what is the path it will prefer? What is the path it will prefer as it moves from B to B? So shall we say that it will prefer a straight line path? Now the primary next question comes, why can't it choose a path of this kind? Or why can't it choose a path of like this? Why the light will prefer to move along the path AB? I think this was the basic, the rectilinear propagation of light. So the light will always prefer a path in which it can traverse the path in shortest time. There's a medium. So what is this yellow color you're seeing? This is a medium. The light will always prefer a path in which it can traverse the path in a shortest time. That one. Now, what is the speed of light? Let it be v. So now if it prefers this particular path, as it can move from A to B in a shortest path in a shortest time. Therefore, it is going to propagate along AB in a straight line, provided if this is in a medium. This is. Now let's do one thing. We will bring two different medium. Then we'll see that what conditions will arise. So there's a medium one. There's a medium two. Let me define. So some reference lines I'm drawing for my sake, and this is the boundary, or what you can call like an interface. So this is the medium one, and this is medium two. So let me okay, the light, it has to know whether the point A and B. Now the point A and B are in different medium. Previously, the points A and B are in same medium. So to traverse this path, it has to choose a path. To move from A to B, it has to choose a path where it will have a shortest time. So definitely it should be a straight line. Now what about here now? So here the speed of light in the first medium will be v1. So it will propagate with a speed, say v1, refractive index mu1. Here I write v1, mu1. Speed of light in second medium is v2. Refractive index is mu2. Let me choose, this is y-axis, this is x-axis. Okay, now will the light will propagate still in straight line? If it moves from one medium to another medium, the answer is no. So the light will, as I said, it will always traverse a path in a shortest time. Means it will traverse the path in which the light will take shortest time. Means it will try to prefer a path. It will prefer a path in which it can traverse in a shortest time. Okay, let's assume that v1 is greater than v2, speed of light in. So definitely this should be the rarer medium. This should be the denser medium. Now, so as it is a rarer medium, so to reach point B, from A to reach point B, it has to travel more in rarer medium than B. Are you getting this one? So what is the basic idea? This is called like a Fermat's principle here. So what that Fermat principle says is like principle of least time. This one. So here I'll write down the Fermat's principle. I'll take it out this, or I'll put it to the corner. This I don't need, so I'll push it to the corner. Yeah. Now, what that Fermat's principle? So let me write that condition: V1 greater than V2. Fermat's principle: light travels between 2 points. Light travels between 2 points in which it will traverse in a shortest time. Light travels between 2 points in which it can light travels along a path, we'll write it, in which it can traverse in shortest time. So preferably here how the path it has to be. So the path or the light will take I will be very surprised sir, why you are making why not AB, why you are suddenly changing the position of this. So enough, we have enough mathematical reason. This is the normal what we can put it here. So let this be the theta 1, let this be theta 2. So that the incident ray, this will call as refracted ray. So this height, let it be HB. So let this be XB. Let this be X. Let this be XA. Let this be HA. Let's have some geometrical considerations. So where do the light will strike? It will strike the boundary, and this is the boundary. This is called like a boundary. So where do it will strike the boundary? It will strike at the point C. There it will bend. So why this bending of ray of light? Due to Fermat's principle, light travels along a path in which it can traverse in shortest time. So it prefers to yeah, it's quite meaningfully it is there here. Light travels along a path in which it can traverse in shortest time. So it has to move from A to B. So rather than preferring this line, the straight line path AOB, so it will travel more in medium 1 than medium 2. So therefore it will bend here. Okay, let's take this one. This is a Feynman's principle. This is a nature's phenomena. So why it is like this means there's a nature's phenomena which we have made observation, and from this observation, like we are going to bring the Snell's law here. So time taken by the light to move from A to B. So shall we say that AC into V1? So it will cover a path length, how much AC in medium 1 with a speed V1. What is the speed of light in this medium V1? It will cover a path length of CB in medium 2. What is the speed of light in second medium? Let it be V2. CB by V2. What is AC further? AC can be write anything. We have a right angle triangle. Are you looking at this one? This will become hypotenuse. So we have a right angle triangle. This is XA, no? From here. No. So from this right angle triangle, what we can write this hypotenuse as like XA plus X whole square root of XA plus whole square plus HA square by V1. So this should be, what can be this? This CB is equal to, this will become hypotenuse for this triangle. So what is this length should be equal to XB minus XC, sorry, XB minus X whole square plus HB square by V2. Now it is going to traverse in a shortest path. So let me differentiate this with respect to x. So this will become 1 by 2 under root of xa plus x whole square plus ha square into v1. This will be into v1. So the derivative of this will be 2 times of xa plus x. As ha is constant, so it will be 0, that one. And with respect to x we derived, so this will be the equation. Now similarly this will be 1 divided by under root of 2 whole square. So then the derivative of this will become 2 times of xb minus x. Looking at this, what is sine theta we can define here? Sine theta 1, now this 2 will get eliminated, xa plus x by O divided by into v1. This will become negative of this derivative, minus of xb minus x. Okay, this will be, now we have to search for the shortest time, no? So it should be minimum. Before that, what is this ratio of these two quantities? Xa plus x will become this horizontal, and this will be the hypotenuse. So this sine theta 1, what we can write here is like a xa plus x by ac. So this everything will become sine theta 1 by v1, sine theta 2 by v2. We are searching for the minimum. So shall we equate for 0? Because we are searching for the minimum time, or for shortest time. So it should be equal to 0. So finally we landed with the equation sine theta 1 by v1 equal to sine theta 2 by v2. Further, what is v1? v1 should be equal to c by mu1. So this will become mu1 sine theta 1 equal to mu2 sine theta 2. So this is the called as Snell's law. So what is theta 1, theta 2? So they are the angle of incidence and angle of refraction. So there's one basic fundamental Snell's law is what we have derived. Our entire rest of ray optics revolves around this formula. Why you are equating for 0? Because the light will always prefer a path in which it can traverse it with the shortest time. So therefore I am equating that for 0, that one. dt by dx, let it be equal to 0. On simplifying this, v1 as c by mu1, v2 as c by mu2, I'll end up with the Snell's law, so which is equal to mu1 sin theta 1 equal to mu2 sin theta. So what are mu1, mu2 sin theta 2? Theta 1 will become angle of incidence. This will become normal. This is a boundary. This is the incident ray. Theta 1 will become angle of incidence. Theta 2 will become angle of refraction. And it obeys the principle of reversibility of light. It's not that if light moves from B to A also, the same condition. It's not that only when light propagates from A to B. Even the light propagates from B to A also, it will try to prefer the shortest, it will prefer a path where it can traverse in the shortest time. So it definitely it will prefer a path BCA. Let's put further. So now if you take let this be a two mediums are there. So there's a medium 1, there's a medium 2. So instead of analyzing now, we'll analyze in terms of the Snell's basic formula. So if a ray of light is incident here, if it is going to bend. So why this bending there, it was, I gave explanation. I'll further clarify things. This is a refracted ray. This is the medium 1, mu 1. Here the light will propagate with the speed v1. Refractive index mu 2, light will propagate with the speed v2. Wavelength of light will be lambda 1, here wavelength of light lambda 2. What about the frequency of light here? F, here F. So this is the medium 2, medium 1. This will be denser, this will be rarer. Then what is the basic Snell's law? The Snell's law, what it says is like mu 1 sine theta 1 equal to mu 2 sine theta 2. As a denser, mu 2 greater than mu 1. What do you expect? Theta 2 should be less than theta 1. So this will become angle of incidence. This will be angle of refraction. This is the normal. This vertical line will become normal. And this will called as boundary or interface between the two mediums here. So what is theta 1? How you define angle of incidence? Angle made by the incident ray with the normal. Theta 2 is called as angle of refraction. Angle made by the refracted ray with the normal. All these angle in the Snell's law, these angles are measured with respect to the normal. So what do you mean by normal? So this is the boundary which will separate two mediums and a line drawn perpendicular to the interface. So boundary is called as a normal. And in the Snell's law, this theta 1, theta 2 are the angle of incidence and angle of reflection measured with respect to the normal. Okay, let's analyze here. Mu 2 greater than mu 1. So what do we expect? V2 less than V1. Lambda 2 less than lambda 1. Frequency of light is going to remain same. So when a ray of light moves from rare to denser medium, it will bend towards normal. And then can we get the deviation suffered by it? If there is no change in medium, it would have propagated this direction. So what is the deviation suffered by the ray? The deviation suffered by the ray is delta. So here can we just bring the deviation? So theta 2 plus delta equal theta 1. So deviation equal to theta 1 minus theta 2. Or angle of incidence minus angle of refraction. Should be the deviation suffered by the ray when it moves from rare to denser. Okay, now similarly, if a ray of light, if it moves from denser to rarer, then we'll see what conditions will arise. Okay, let this be the normal, not visible. Okay, let this be the normal. What is a boundary? There is a boundary. Now the ray of light is incident from denser to rare medium. Now the reflected light will bend away from normal. This is the incident light. This is the theta 1. This is the angle of refraction theta 2. This is a refracted ray and this is a normal. Now Okay, I'll do one thing, theta 3, theta 4 let me call. So this is a denser medium, this is a rarer medium. Here mu 3, this is mu 4. Here the wavelength of light lambda 3, speed v3, frequency f. Wavelength of light here lambda 4, speed is v4, frequency of light will be f. Frequency will not change as it propagates from one medium to another medium. Then again we'll apply the basic same Snell's law. What the Snell's law says is like mu 3 sine theta 3 should be equal to mu 4 sine theta 4. Mu 3 into angle of incidence sine theta 3 should be equal to mu 4 into angle of refraction sine theta 4. No, which is a denser, mu 3 greater than mu 4, v3 less than v4, lambda 3 less than lambda 4. Then we'll go for the deviation suffered by the ray. What is the deviation here? The deviation will come. This is a deviation. So what is the deviation equal to in this case? The deviation should be equal to theta 4 minus theta 3. So when a ray of light moves from denser to rarer medium, the deviation will be angle of refraction minus angle of incidence. When a ray moves from rarer to denser, the deviation will be angle of incidence minus angle of refraction. Okay, like this, the primary conditions is what we define here. Now, why do the ray of light will bend? As already told you, the light wants to move from A to B. So it could have gone, so why it will not traverse straight? Again, it has to move from A to B in a shortest time. So therefore the light will bend here. It will move more in the rarer medium than in the denser medium. To move between 2 points, if a medium encounters, like previous one, the light wants to propagate from A to B. Then it will prefer a path so that it can traverse in a shortest time. So therefore it has to propagate more in the rarer medium than the denser medium. Based on this is what the Snell's law is derived, based on Fermat's principle. That only I'm just explaining through the diagrams here. The light moving from rarer to denser. These are the 2 points. Why can't it just go straight? No. According to Fermat's principle, the light will propagate from A to B along a path which it takes the shortest time. So therefore, this is a path it will prefer. It has to propagate more in the rarer medium than denser medium. That's why it will prefer this path. Okay, this is about the bending of ray of light when it moves from rarer to denser to denser. So what is the conclusion? Ray of light bends towards normal of the refracted ray. The refracted ray bends towards normal when it moves from rarer to denser. Same thing. The refracted ray of light bends away from normal when it moves from denser to rarer. Okay, now, so when a ray of light moves from rarer to denser, it will bend towards normal. When it moves from denser to rarer, it will bend away from the normal. Sir, okay, you are just showing it on like some diagrams you are drawn. Okay, Fermat's principle will agree it. Still, can you give a better explanation? Yes, we'll go for a better explanation. We'll talk about in terms of the wavefront. Suppose if this is the boundary and this is the normal. Okay, here I'll bring the wavefront idea. Now, what are these red color lines? They are the wavefront. What do you mean by wavefront? Next question comes, what is a wavefront? It's a plane in which all particles will have same phase. The light is propagating like this. So let me choose 2 points like A and B. So what is it? This is a medium one. Refractiveness mu1, and it will propagate with a speed v1. So here both these particles will have same speed. So what is Va equal to Vb equal to V1? When the same particle arrives here, it will enter into medium 2, refractance mu2. So here speed is how much? V1 equal to C by mu1. Here V2 equal to C by mu2. I'll say this is a rarer. Then what we can say? V1 greater than V2. Now look at the particle B and D. Now the B has entered into the medium. So what is the speed of this? Will become V2. And the A is yet to enter into medium 2. So it will have a speed V1. So now what will happen to the wavefront here now? The point B on the wavefront will have less speed than this in a given interval of time. The wavefront here will be like this. So in a given interval of time, the V2 is less than V1. So in a given interval of time, the point B of a wavefront will cover less time than the point A on the wavefront, less distance. You calculate this one. So this is V1 greater than V2. In a given interval of time, the A will traverse more path than B. Okay, let me put it in this way. Then afterwards, both A and B will enter the same region. So then both will have same speed and the wavefront again will become parallel to each other. So here it will propagate with a speed V2. So the entire discussion what we have to do is like here at this particular point we have to do it. Here the point B will have a speed V2 whereas this will have a speed V1. In a given time the A will cover more distance than B. So here the distance covered is less, here it is more because the speed is V1 here of the point of the wavefront. Here the speed of the point B will be the point B will lie in the now denser medium. It will have less speed. So in a given time it will traverse the less distance. So therefore the wavefront will bend. This equation what we can give. If you are talking in terms of the wavefront, if you bring the idea of the wavefront, as you analyze in this particular way. I'll give in detailed diagram. So some of you may find this very difficult. There's a wave it has entered. It is like this. Same thing. I'll magnify the diagram. That's all here. So you can see clearly now both will have same speed. Now also both will have same speed. Now very next moment you can see that it is going to have the speed v2, so the wavefront will bend. Then also you can see that. No, again, okay, no problem, that one. They will have same speed. This region is something very important. Here, what is the speed of the wave? Point B and A will be same. No, will be same. Very next moment, the speed of B will be less compared to A. In a given interval of time, this will cover more path, this will cover less path. So therefore, the wavefront will bend. This only I just magnified it. V1, 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 V1. It will be V2, V1, V2, V1. Now V2, V2. So V1 greater than V2. Getting the idea? So why the ray of light should bend towards normal when it moves from rare to denser medium? There's a basic condition. We can put it here. Similarly, what will be the when a ray of light moves from denser to rare medium? We'll analyze in terms of wavefront. I think I can't. Okay, I'll go for another page. There's a boundary. There's an incident ray. Let me choose this is denser medium and this one is rarer medium. Now the ray of light, both the points on the wavefront are in same medium. Let it be in this way. Now it will encounter a boundary here. So now this is a denser medium, mu2, this is mu1. So v2, this is speed of the wave here will be v2. v2 will be less than v1. Now this particular point now will enter into the rare medium. This will be still in denser medium. So it should be like this. It will move forward. Finally, it will arrive. Draw a line perpendicular to it. Now look at this particular point. Some other color. Here they were having a speed v2, v2. Now this is v2, this v2. This will have speed v1, v1. v1 in fact greater than v2. You can see from the diagram, in a given interval of time, this point will cover less distance than this one. So the wavefront has to bend here now. Once they enter into, again you can see here, this is v2, v1. Then v1, v1. So when a ray of light moves from denser to rare medium, it should bend away from normal. The reason for that, this particular point A, this is a point B. The B will now traverse in the rare medium. So in a given interval of time, it has to cover more length, more distance than the A. So you can see this distance and this distance will be more than this. So therefore the wavefront has to bend. Okay, the bending of ray of light. Why it has to be? So in terms of wavefront, what we can put here. So here the light will propagate with a speed v1. Here it was speed v2. Okay, like this, the Snell's law, uh, we can give a absolute explanation in detail, like in terms of wavefront or using the Fermat's principle. We can express the quantities here. Okay, after this, we will have some small look over the animation. Now you can basically look at it. So there's a point source which will generate the waves here. The point source which will generate the waves. Now the particular wave has to move from this particular point, so it has to reach this one. So why can't it go in a straight line like this here? So then it will traverse a path in which it can take the least time. The time of traverse to be least. So therefore the light what happen will propagate here. Here it will bend. You can see the wavefront bending here. The wavefront itself, because there's a medium one. So we can see that the ray of light moving here, when it moves from medium 1 to medium 2, it starts bending here. The wavefront itself will bend. As the ray moves from rare to denser medium, so the wavefront is going to bend here. So this for point source spherical wavefront, what will happen the spherical wavefront when it strikes the boundary? Is what we have this particular animation. Okay, there I just took the plane wavefront. Here for spherical wavefront is what is being shown here. So you can see this particular thing. So the ray of light moving here. After refraction, it will bend. It will bend towards normal. So this shows that the ray is moving from rare to the denser medium. Okay, this one, yeah. Okay, now we'll take the next situation. If this particular thing, if it encounters the multiple boundaries, how do the Snell's law will be still applicable in these situations? That will try to analyze here. So let's have I think that one. So a ray of light here. Let the refractive index be mu1. Refractive index of this be mu2, mu3. This is mu4. Let this be mu5. This is the normal. Now this will become the normal. Now the ray of light is incident. So after refraction, it will bend like this. This is theta 2, theta 1. Now this will become the normal for the 2 and 3 interface. So this will become theta 2. Now let the ray of light is moving from, say, denser to rarer. It will undergo refraction. It will bend away from normal, theta 3, theta 3. Now the ray of light is moving from one medium to another medium. So let it be again the moving from rare to denser. So it will bend, and let this angle be theta 4, theta 4. This is theta 5. So if a ray of light encounters a multiple interfaces, what method has to be applied here? So applying sticking with the basic Snell's law, at this interface 1 and 2, here, mu1 sine theta 1 should be equal to mu2 sine theta 2. At this interface, mu2 sine theta 2 sine theta 3. At this interface, mu3 sine theta 4. Then at this interface, mu4 sine theta 5. Multiple boundaries are there, so we can take care of this basic condition. Now, equating all this, so finally what we can write? Mu1 sine theta 1 is equal to mu2 sine theta 2, or mu 2 sine theta 2 equal to mu 3 sine theta 3 equal to mu 4 sine theta 4 equal to mu 5 sine theta 5. Altogether, mu sine theta is equal to constant. There is nothing but again the same Snell's law. If mu1 is equal to mu 5, special condition, if mu1 equal to mu 5, then theta 1 equal to theta 5. I'll separately bring that one. So what about this? This will be the ray, it has to traverse path like this. Look at the arrows, I'm showing it. Now finally, sir, how these two rays are, need not be parallel. There's the incident ray, there's the incident ray refracted. Again, this will become incident ray for boundary 2 and 3 for interface 2 and 3. Now this will become incident, this will be refracted. Now this will become incident, this will be refracted. So like this, the ray will undergo multiple refractions and finally will emerge into the medium phi. How theta phi, theta 1 are related? So we can directly write Snell's law between these 2 points. Yeah, mu1 sin theta 1 equal mu phi sin. Altogether, mu sin theta equal constant. Let's bring a special case where if mu1 equal to mu phi, if mu1 equal to mu phi, very specifically, I'll put it here. So in that case, the ray will emerge parallel. So if you look at this particular thing, this section ray, you bring it here, it will become parallel to that. The emergent ray will be parallel. I'll realign the diagram. This condition is very, 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 very important for us. This is theta phi. When do this will, so these two are, this is the emergent ray. This is the incident ray. Yeah. So in this incident ray and the emergent ray, they'll be parallel. When that will happen? When mu1 equal to mu phi, theta 1 equal to theta phi. No deviation, there won't be any deviation. This is something very, very important here. Even it will undergo multiple refractions, the emergent ray will become parallel to the incident ray. Okay, so this is one primary condition is what we are going to put it here. So like a n number of slabs are there, we can keep on right? Yes, that's what I shown no earlier. Mu1 sin theta 1 equal mu2 sin theta 2. Here mu2 sin theta equal mu3 sin theta 3. Here this, what is this angle of refraction? That will become angle of incidence. So mu3 sin theta 3 equal to mu4 sin theta 4. So mu4 sin theta 4 equal to mu5 sin theta 5. Or mu sin theta equal to constant. That's what the basic Snell's law what it is telling. All these angles are measured with respect to what? With respect to the normal. How to identify normal? If this is the interface, then this will be the normal. Again, this is a boundary or interface. So draw a perpendicular to the boundary. That will become normal. And the angle of incidence, angle of refraction, we should measure with respect to the normal, not with respect to the boundary. So there's a overall the basic idea of the Snell's law is what I just brought here. Okay, no. So I'll let me end up the class. Okay, there's about only theoretical one. In the coming class, we'll see that how this application of this will come. Okay, kids, like we had the discussion on the derivation of the Snell's law. That was the thing which we are supposed to discuss that one. So what you are saying, we took help of the Fermat's principle. There we derived an expression for the Snell's law using that one. So what do that Fermat's principle says that? So according to the Fermat's principle, the light will always prefer to move, will always tries to prefer to traverse a path which will lead to least time. It will always move between 2 points where the time of travel will be least here. This was the Fermat's principle. Based on the Fermat's principle, we applied it and we brought the Snell's law. So what the Snell's law will tell that when a ray moves from rare to denser, medium, denser to rarer, how do the path of the ray, the why the ray will bend. Therefore, the explanation is what we give. So when a ray of light moves from rare to denser, the refractor will bend towards normal. When a ray of light moves from denser to rarer, the refractor ray will bend away from normal. Therefore, the explanation using the wavefront also, we have explained it. Then if the multiple interfaces come, can we apply the Snell's law as mu sine theta equal to constant? So this is about the introductory part of the Snell's law. The coming class will take the application of Snell's law, how the various, where all we can apply the Snell's law and how we can find out the unknown things. Okay, thank you all of you. We'll meet in the next coming class. Okay, bye. See you all of you. Take care.